name is Catherine Stalter, and I'm one of the people you'll be seeing on this videotape reviewing every aspect of the new integrated math curriculum. We are backed by a team of educators who have put together a powerful learning tool incorporating computerized techniques which can quickly and efficiently allow us to visualize math concepts for you. Think of us as your own personal math tutors, available whenever you'd like to review concepts and techniques in math. Before we get started, I have some advice that can help you get the maximum benefit from this tape. First of all, this material is designed to complement, not replace classroom instruction. Unless you have exposure to these concepts in a classroom setting with a good teacher and a good textbook, you're likely to find the pace of this presentation too rapid. The key word here is review. Very few people will be able to use the videotape in place of formal classroom instruction. Next, please, don't fall into the trap of regarding this as being similar to any other kind of television. We are all in the habit of letting our brains sort of go to sleep whenever we're in front of the tube. The material presented on this tape concentrates weeks of work into just a few minutes. You must be ready to concentrate on what is shown and said. Take frequent breaks. Perhaps 20 minutes at a time is as much as most people can devote to material like this without at least a short change of pace. Whenever you feel yourself starting to lose concentration, it's time to turn off your machine. Get some fresh air, do some physical exercise, or perhaps get something to eat. The important point is you're in control. We'll always be here when you get back. Which is my next point. In order to really get the most from the videotape, you should get used to the idea of using the controls of your VCR to help you get the information you need. Use your remote control if you have one, or sit close to the machine if you don't. Be ready to pause, rewind, and replay sections over until you are comfortable with the concepts we present. In connection with that, have a pencil and paper handy. You should feel free to pause your VCR and write out some of the material we'll be presenting for yourself. Working out problems for yourself will increase your mastery of the topics. Try to make the experience of using this tape as interactive as possible. If you remain a passive viewer, I'm afraid this will be less valuable to you. If you have the VTS manual, the workbook which accompanies our videocassette tape, use it extensively in your review. You'll find that your mastery of this material will rapidly increase in this way. One last comment. As you go through the tape, write down the counter number from your VCR for those portions of the tape that you think you'll need to review later on, so you'll be able to find things easily on the tape later. Remember to set your VCR counter to 0 each time you use the tape. So, while you're getting ready, set right near your VCR with a pencil and some paper, you can shut off your machine and take your first break before we begin our first review topic.
To help us improve our ability to think clearly, we study a branch of mathematics called logic, which deals with the rules of reasoning. In logic, we concern ourselves with a very special kind of sentence, a sentence that can be judged true or false, but not both. Such a sentence is called a statement. Here are some examples that cannot be judged true or false, and therefore are not considered logical statements. What is today's date is a question, and questions cannot be judged true or false. He is here and x plus 2 equals 5 are examples of open sentences, which cannot be judged true or false. Open sentences are sentences which contain variables, words or symbols which may be replaced by any member of some appropriate set. In the sentence, he is here, he is a variable. And in the sentence, x plus 2 equals 5, x is a variable. Today is Tuesday is a statement. It is true or false. The truth or falsity of a statement is its truth value. Statements are the building blocks of logic. It is convenient to use letters to represent statements. For example, we say, let P represent the statement, today is Tuesday. If we wanted to say today is not Tuesday, or it is not true that today is Tuesday, we say not P and symbolize not P thusly. If P represents it is not raining today, then not P would mean it is false that it is not raining today, or more simply, it is raining today. In general, if P represents a statement, then not P is the negation of that statement. Also, P is the negation of not P. That is, P means not P. If P represents a true statement, then not P represents a false statement. And if P represents a false statement, then not P would represent a true statement. We can summarize these ideas in tables called truth tables. For example, the truth table for negation would look like this. We use two columns, one for P and one for not P. If P is true, then not P is false. And if P is false, then not P is true. Remember, every statement is true or false, but not both. And the negation of a true statement is false, and the negation of a false statement is true. Two simple statements can be connected together in different ways to form what we call compound statements. For instance, if P represents the statement, today is Sunday, and Q represents the statement, I went to the movies, we can combine the two simple statements by using the word and. We then have the compound statement, today is Sunday, and I went to the movies, symbolized as P and Q. The symbol for and, as you can see, looks like an upside-down V, although we may think of it as an A for and, without the bar in the middle. When two statements are connected by the word and, each of them is called a conjunct, and the compound statement is called a conjunction. Thus, P and Q is a conjunction, P is a conjunct, and Q is a conjunct. Let's examine the conjunction, today is Sunday, and I went to the movies. If both statements are true, that is, if today is Sunday, and if I did go to the movies, then the conjunction is true. What if it is not Sunday, but I did go to the movies? Have I told the truth? The answer is no. The conjunction is false. In the same way, the conjunction would be false if today is Sunday, but I did not go to the movies. And the conjunction would be false if today is not Sunday, and I did not go to the movies. So we see that a conjunction is true only when both conjuncts are true, and in no other case. Let's summarize our findings in a truth table for conjunction. This time, we need three columns for P, Q, and P and Q. Either P and Q can both be true, or P can be true and Q can be false, or P can be false and Q can be true, or finally, both P and Q can be false. We have said that a conjunction is true only when both conjuncts are true. And so, the truth table looks like this. When P is true and Q is true, P and Q is true. When P is true and Q is false, P and Q is false. When P is false and Q is true, P and Q is false. And when P is false and Q is false, P and Q is false. And this is what our completed truth table for conjunction looks like. The word or is a funny word. In the Old West, they used to have signs saying, wanted, dead or alive. That, of course, meant either dead or alive, but not both, because a person is either dead or alive. In the same way, when we judge a statement true or false, we mean one or the other, but not both. However, sometimes or can mean either one possibility, or the other, or both. For instance, if you say, I will have apple pie or vanilla ice cream for dessert, you could possibly have pie or ice cream or both for dessert. Or if a store says we accept Visa or MasterCard, they would accept one or the other or both. In logic, we use or to connect two statements in this second way, to mean one statement or the other statement or both statements. Just as we used and to combine statements, we can use or also to form a compound statement. If P represents I will watch television and Q represents I will go to the movies, then we can say I will watch television or I will go to the movies, and write it in symbols as P or Q. As you can see, the symbol for or looks like a V. Be sure not to confuse it with the symbol for and, which looks like an A without the bar in the middle. An or statement is called a disjunction, and each component or part of a disjunction is called a disjunct. Let's examine the disjunction we've made. If I watch television but don't go to the movies, I've told the truth, haven't I? Because I said I would do one or the other. In the same way, if I don't watch television but I go to the movies, I've told the truth. What if I watch television and go to the movies also? Have I lied? Of course not. I said I would do one or the other, but that doesn't mean I can't do both. So I've still told the truth, even if I do both. Thus, the only time a disjunction is false is when both disjuncts are false. In other words, if I don't watch television and I don't go to the movies, then I've lied, and the disjunction is false. Let's set up a truth table for disjunction. Again, there are three columns. We head the columns P, Q, and P or Q. Now, P and Q can both be true, or P can be true and Q can be false, or P can be false and Q can be true, or both P and Q can be false. We have said that the only time a disjunction is false is when both disjuncts are false. So, we fill in our table as follows. When P is true and Q is true, P or Q is true. When P is true and Q is false, P or Q is still true. When P is false and Q is true, P or Q is still true. And finally, when P is false and Q is false, P or Q is finally false. And this is what our completed table for disjunction looks like. We're all familiar with the kind of statement that goes like this. If you finish your homework, then you can watch television. Such a statement is called a conditional because it says that something will happen on condition that something else happens first. Now, if we let P represent you finish your homework and Q represent you can watch television, then we may represent the conditional if you finish your homework, then you can watch television like this. This is read, if P, then Q, or P implies Q, or Q if P. P is called the antecedent or hypothesis of the conditional, and Q is called the consequent or conclusion of the conditional. As you can see, the symbol for the conditional is an arrow. Let's examine the conditional we used as an example. If you finish your homework, then you can watch television. Now suppose you finish your homework and are then permitted to watch television. In this case, both the antecedent and the consequent would be true, and the conditional itself would, of course, be true. What if you finish your homework, but you are not permitted to watch television? In this case, the antecedent would be true, and the consequent would be false, and the conditional statement would be false, because you would have been lied to. Now, what if you don't finish your homework, and you're permitted to watch television anyway? Well, in this case, the antecedent would be false, and the consequent would be true, and the conditional would have to be considered true, because you weren't lied to since you didn't fulfill the requirement of completing your homework. In the same way, if you don't finish your homework and you're not permitted to watch television, then both the antecedent and the consequent would be false, but the conditional would have to be considered true, because you weren't lied to since you didn't satisfy the condition. Therefore, a conditional is false only when the antecedent is true and the consequent is false. Let's summarize our findings in a truth table. By this time, we know how to fill in the first two columns, and since we know that a conditional, if P then Q, is false only when P is true and Q is false, we can fill in the rest of the table as follows. If P is true and Q is true, then the conditional, if P then Q, is true. If P is true and Q is false, then the conditional is false, and this is the only time it's false. If P is false and Q is true, the conditional is still true. And if P is false and Q is false, the conditional nevertheless remains true. You should be extra careful not to think that the antecedent always comes at the beginning of a conditional statement. For example, the statement about homework could have been written, "You can watch television if you finish your homework." In this case, the antecedent, the part with the if in front of it, follows the consequent. Given a conditional, if P then Q, there are other statements which are related to it. If we take the conditional, if P then Q, and switch the antecedent and consequent around, we get a new conditional that looks like this: if Q, then P. This new conditional, in which we reversed the role of P and Q, is called the converse of the original conditional, and it may or may not have the same truth value as the original conditional. Suppose P represents today is Sunday, and Q represents tomorrow is Monday. If P then Q would translate as, if today is Sunday, then tomorrow is Monday. Do you know what the converse would be? Just reverse P and Q, and you get if Q then P. This translates as, if tomorrow is Monday, then today is Sunday. Now, in this example, the converse has the same truth value as the original conditional. But let's look at another example. Let P represent Sam is an elephant, and let Q represent Sam has 4 legs. The conditional, if P then Q, is, if Sam is an elephant, then Sam has 4 legs. Now, assume that Sam is a normal elephant and has 4 legs. The converse, if Q then P, is, if Sam has 4 legs, then Sam is an elephant. Now, here, it is clear that the original conditional is true, but the converse is false, because Sam could be any 4-legged animal. And so we see that the converse of a conditional may or may not have the same truth value as the original conditional. If we negate the antecedent and the consequent of the conditional if P then Q, we get if not P, then not Q, which is called the inverse of the conditional. Using the previous example, the inverse of the conditional, if Sam is an elephant, then Sam has 4 legs, is, if Sam is not an elephant, then Sam does not have 4 legs. Now, clearly, the inverse here is false, as Sam does not have to be an elephant to have 4 legs. And so we see that the inverse of a conditional, like the converse, may or may not have the same truth value as the original conditional. And finally, there is one more thing we can do with if P then Q, and that is called the contrapositive. If we negate both P and Q of the conditional if P then Q, and then switch the order around, we obtain if not Q, then not P, and that is known as the contrapositive of the original conditional. Again, using our example, the contrapositive of if Sam is an elephant, then Sam has 4 legs is if Sam does not have 4 legs, then Sam is not an elephant. Since it's true that a normal elephant has 4 legs, then it would be true that if Sam does not have 4 legs, then Sam is not an elephant. Indeed, we can prove by using truth tables that the contrapositive has the same truth values as the original conditional. We set up our truth table with the following 6 columns. P, Q, not P, not Q, if P then Q, and if not Q, then not P. Now by this time we can set up our first 2 columns rather rapidly. We know that P and Q can both be true, or that P can be true and Q can be false, or that P can be false and Q can be true, or finally that both P and Q can be false. Our third column, the negation of P or not P, depends of course on P. If P is true, then its negation is false. If P is true, then its negation is false. And if P is false, then its negation is true, and if P is false, its negation is true. Now we go to the fourth column, the negation of Q or not Q. To fill this out, we have to look at the second column, Q. If P is true, its negation is false. If P is false, its negation is true. And if Q is true, then its negation is false. And finally, if Q is false, its negation is true. And now we look at the next column, the conditional if P then Q. We know that this is false only when P is true and Q is false. That is, when the antecedent is true and the consequent is false. Therefore, we can put false in right here, and we can fill true in the other spaces as follows. And now we look at the last column, the contrapositive, if not Q, then not P. To fill this in, we have to look at not Q and not P. Not Q is our antecedent, and not P is our consequent. The only time this would be false is if the antecedent, not Q, is true, and the consequent, not P, is false. So we can put false in right here, and we can fit true in the other spaces as follows. The table shows us that whenever if P, then Q is true, if not Q, then not P is true. And whenever if P, then Q is false, if not Q, then not P is false. Thus, the contrapositive, if not Q, then not P, always has the same truth value as the original conditional. When 2 statements have the same truth values, the 2 statements are said to be equivalent. Thus, a conditional is equivalent to its contrapositive. If we combine a conditional and its converse as a conjunction, we write if P, then Q, and if Q, then P. This compound statement is called a biconditional and is symbolized by a double arrow. The biconditional is read if P, then Q, and if Q, then P. It is also read P if and only if Q. Let's construct a truth table for the biconditional. There are 5 columns in this truth table. P, Q, if P then Q, if Q then P, and finally, if P then Q and if Q then P, or P if and only if Q. We've already filled in the first 2 columns because you're probably quite familiar with this by now. So let's go to the third column, if P then Q. We know that this is false only when P is true and Q is false. So let's put false in here, and let's put true in the other spaces. And now let's go to the fourth column, if Q then P, the converse. We know that this is true only when Q is true and P is false because Q is the antecedent and P is the consequent. So let's put false here, and let's put true in all the other spaces. And now our final column. This is a conjunction, and we know that a conjunction is true only if both conjuncts are true. So, when this is true and this is true, then the conjunction is true. When this is false and this is true, the conjunction is false. When this is true and this is false, once again the conjunction is false. And when this is true and this is true, the conjunction is true. Notice that the biconditional P if and only if Q is true when P and Q are both true or both false. Some biconditionals are always true. Let's look at a truth table for such a biconditional. Our 7 headings are P, Q, not P, not Q, if P then Q, the contrapositive, if not Q then not P, and finally the biconditional, if P then Q, if and only if not Q then not P. Well, we have filled in the first 6 headings already because you're already familiar with that. So let's just concentrate on the last heading. This is the biconditional, and we mentioned that this is true when both of its component parts have the same truth value, either both true or both false. Since these are both true, then this is true. Since these are both false, then the biconditional is true. Since these are both true, this is true. And since these are both true, the biconditional is again true. The last column shows us that the biconditional, if P then Q, if and only if not Q then not P, is always true. Every entry in the last column is true because the components of the biconditional, if P then Q, and if not Q then not P, are always both true or both false. When every truth value in the last column of a truth table is true, the statement at the top of the column is called a tautology. Thus, the biconditional, if P then Q, if and only if not Q then not P, is a tautology. A tautology is defined as a statement which is always true no matter what truth values are assigned to its component parts. We can also say that a statement is a tautology if in the truth table for that statement, every entry in the final column is true.
We sincerely hope that you found this tape useful. And for all of us here at VTS, we wish you the very best of luck in all of your academic endeavors.